We have seen in previous modules that the position of the metacenter, m, is related to the position of the center of buoyancy, b. The distance or height of the metacenter, m, from the keel, k, is called kilometers. Kilometers for various drafts are tabulated and included in the hydrostatic tables in the vessel's stability booklet. In this lesson, we are concerned in finding grams. The transverse stability of a vessel depends, among other things, on the vertical position of the vessel's center of gravity, g, in relation to the metacenter, m. Center of gravity, g, is a movable point. That is to say, it moves if weights are added to, removed from or transferred within the ship. The metacenter is also a movable point. At angles of heel beyond 10 degrees, the vertically upward force of buoyancy intersects the ship's center line at various points. The keel, k, is fixed and is used as a reference in some ships. Distance is used in stability calculations. The height of m above the keel is kilometers. The height of g above the keel is kilograms. Here is a typical hydrostatic tables for a big ship. Let's take a look at the parts we used to calculate GM. In the first column, we see draft ext. This means draft extreme and is measured from the bottom of the keel plate. In the second column, we see disp full means displacement full and shows the total displacement of the vessel corresponding to that draft at the table density. The stability booklet will clearly indicate the water density assumed in calculating the displacement. It is usually assumed to be salt water, that is 1.025 metric tons per cubic meter, but could be different. In the column third from right, TKM means transverse km. The effort used to obtain the draft will depend on how critical the calculation is. If we are just checking during the load, we can just use the midship draft. If we need more accuracy, we take forward, midship and aft, port and starboard and find an average or mean draft. For this module we are using a draft of 8.10 meters. We go into the hydrostatic tables to find km with the draft 8.10 meters. The displacement at 8.10 meters draft is 38,725.8 metric tons. The distance from the metacenter to the keel at this draft is 14.44 meters. Here we see the draft from waterline to the keel. We also see the km for that draft as taken from the hydrostatic tables. Here we see g added to the previous diagram. Let's remind ourselves about some things about g. G is the position of the resultant center of gravity of the ship. G is dependent on the distribution of weights on board. Gm is a measure of initial stability and must be determined to demonstrate compliance with stability criteria. It is necessary to determine the vertical position kg in order to find Gm. Here is how we determine of the vessel's kg by using moments about the keel. The kg of the lightship was determined by the inclining experiment or approved alternative. Every weight added to or taken from the vessel will affect the kg if every weight is placed in specific locations. Each item's center of gravity above the keel is known or can be found. For example, fuel in a double bottom tank. The height above the keel of the center of volume of the tank is known. The kg, even for a partially filled tank, can be determined from the dimensions and characteristics of the tank. Practically, we cannot find the exact kg of everything. For example, in a container ship, we can find the kg for the slot we put a container in but not know how the cargo and weights within the container are distributed. Similarly for stores, the location of each spare machinery part is not required. Usually we reuse the same kg for stores every time. Each weight is multiplied by its kg, resulting in a moment about the keel, specific for that weight and its location. Starting with the weight of the lightship displacement 5,000 metric tons multiplied by kg 6.0 meters giving a moment of 30,000 ton meters. Stores equals 300 metric tons multiplied by kg 9.0 meters giving a moment of 2,700 ton meters. Freshwater is 200 metric tons multiplied by kg equals 5.5 meters giving a moment of 1,100 ton meters. Fuel 500 metric tons multiplied by kg equals 1.2 meters giving a moment of 600 ton meters. Cargo space 1 has 4,000 metric tons multiplied by kg equals 4.0 meters giving a moment of 16,000 ton meters. Cargo space 2 has 5,000 metric tons multiplied by kg equals 5.0 meters giving a moment of 25,000 ton meters. Cargo space 3 equals 5,000 metric tons multiplied by kg equals 5.0 meters giving a moment of 25,000 ton meters. The sum of all these moments is then divided by the total weight, resulting in a new kg. The sum of all the moments in the example is 100,400 ton-meters. Then total weight is 20,000 metric tons. 100,400 divided by 20,000 gives a resulting kg of approximately 5 meters. Kg in the example is 5.0 meters. If the km for the observed draft and displacement is 7.25 meters, km minus kg equals 7.25-5.0 equals gm equals 2.25 meters.